Yeah. Hello all. In my previous lecture, I discussed one of the classification of the material, that is conductor and current flow in a conductor, and effect of drift velocity due to applied electric field. This is I covered in last class. In this class, I am going to cover current density in a conductor. Right? Now heading current density in a conductor, that is in bracket J. So before calculating the current density in a conductor, first I can define what is current density. Current density is nothing but current per unit area, right? To calculate the current density in a conductor, actually first consider a conductor which is having a length L and area A and concentration N. Yeah. Now I can define charge density in a conductor first before calculating current density. So here, what is charge density here? Charge density is nothing but charge per unit volume. So which is equal to Ne. What is this N? N is nothing but free electron concentration or number of electrons per unit volume. N is nothing but number of electrons per unit volume. Right? Now here, how it will become Ne actually rho V equal to, if you multiply with both sides and charge of an electron. Now what is this? N into E, capital N into E, this is nothing but the total charge, right? The total charge per unit volume is nothing but what actually rho V. Now rho V equal to how much? Ne, right? Now after defining charge density, now I can define the current in a conductor. What is current actually? So current is nothing but charge per unit time, or we can also say rate of change of charge with respect to the time also be current. Okay. Now tell me what will be the charge in terms of volume charge density actually? Rho V into volume by T. What is the rho V actually in terms of concentration? N into E. What is the volume actually here? Length into area by time, right? Now what is this? L by T, mean distance by mean time is nothing but what it is? It's simply a drift velocity, right? Now what is I equal to? I equal to N into E into Vd into A. But what is current density actually here? The current density is nothing but current per unit area, so which is equal to N into E into Vd. This is what actually current density in a conductor. Now here this is the current density in terms of what actually? Drift velocity. Now I can define current density in terms of applied electric field, that is J equal to I by A, which is equal to N into E into mu into E. Right. This is the current density in terms of applied electric field. Now here I can define a sigma. What is sigma here? Sigma is nothing but conductivity, which is equal to N into E into mu. Then what it is actually? J equal to sigma E. J equal to sigma E is nothing but what it is? This is the Ohm's law for field theory, right? Or it is also called as first form of Ohm's law. right? Now, this is the current density in terms of applied electric field, right? Now here I can also define the Ohm's law in terms of circuit theory. Now here, what is J actually here? J is nothing but current per unit area. What is sigma in terms of resistivity? 1 by rho. So conductivity is nothing but reciprocal of resistivity. What is the electric field in terms of voltage actually? Voltage per unit distance. Now what it is actually, so V equal to rho L by A into I. Let R equal to rho L by A. Right? Now what is the V actually here? V is nothing but Ri. What is this? V equal to Ri. This is nothing but Ohm's law for what actually? Circuit theory. Right? So this is the current density in a conductor. Calculate. Sorry. Copy. Now write down an example on this topic. Yeah, in your workbook, question number 3. Classroom workbook, question number 3. Write down a question. A copper wire of length 300 meters, and diameter of 1 millimeter, and has a resistance of 6.5 ohms. If concentration of the free electron in copper wire is 8.4 into 10 power 28 per meter cube, and a current of 2 ampere is passing through the wire. Calculate the first bit. Conductivity. Second bit. Mobility. Third bit. Drift velocity. Right. So here they given a copper wire, right? Of length, they given a copper wire of length how much? 300 meters. Also they given a diameter. Actually. How much? 1 millimeter, and has a resistance 6.5 ohms, and has a concentration N equal to 8.4 into 10 to the power of 28. Right? So 2 ampere current is passing through this copper wire. Right? Then calculate conductivity. Yeah. First we want to calculate the conductivity. Yeah. How to calculate conductivity actually? See here. First we know resistance. What is the resistance actually? Resistance is nothing but rho L by A. Right? Now, here what is the rho in terms of conductivity actually? 1 by sigma. L by sigma into A. So from this, what is sigma here? The sigma equal to L by R into A. What is the, when length actually here? 300 meters, right? 300 by resistance, that is 6.5 into area. Area is nothing but pi R square. Actually, they given a diameter actually. In terms of radius, what it is actually half of the diameter. That is radius equal to half of the diameter. That is 0.5 into 10 to the power of -3 meters. right? Now substitute R value 300 by 6.5 into pi into R. R is nothing but 0.5 into 10 to the power of minus 3 whole square. So which is equal to about 0.58 into 10 to the power of 8 ohm meter whole power inverse. This is the conductivity. And the next bit, what is the next bit actually here? Mobility, we want to calculate, right? What is the relation between mobility and conductivity actually? Sigma equal to N into E into mu, right? From this, mu equal to sigma by Ne. What is the sigma value here actually? Sigma value is what we have, how much? 0.58 into 10 to the power of 8 by free electron concentration. How much it is? 8.4 into 10 to the power of 28 into charge of electron 1.6 into 10 power minus 19. Then what is the mobility value here? 4.3 into 10 to the power of minus 3 units meter square per volt second. This is the mobility. And the third bit, drift velocity. What is the relation between drift velocity and current density? Actually, J equal to N into E into Vd, right? Now from this, what about Vd here? Actually, the Vd is nothing but J by Ne. What is the J in terms of current actually here? I by A into Ne, right? What is the I here actually? I is nothing but 2 amperes by area. Area is nothing but pi into R square, that is 0.5 into 10 to the power of minus 3 whole square into concentration 8.4 into 10 to the power of 28 into charge of electron 1.6 into 10 power minus 19. The value is 1.89 into 10 to the power of minus 4. This is the conductivity and mobility and drift velocity, right? Copy. Next topic. Temperature effect on mobility in a conductor. Yeah. See, in case of conductor, how mobility is affected due to temperature. See here, as temperature is increased, what about the mobility here? The mobility is decreased due to lattice scattering. Right? What is lattice scattering? Now see here, as temperature is increased now, then what happened? Thermal energy is supplied to the conductor is increased. Thermal energy supplied to conductor is increased, right? Thermal energy supplied to the conductor is increased means what about the vibrations in a lattice actually? Vibrations in a lattice is increased, right? If vibrations in a lattice is increased, it means what about the chance of collisions increases? Chance of collisions is increases. If chance of collisions increases means what about the mean time actually here? The mean time is decreased. If the mean time is decreased, that means what about the mobility here? Decreased. The mobility is decreased. Right? Now what is lattice scattering here? Here the mobility is decreased due to increasing of vibrations in a lattice is called as what actually? Lattice scattering. Right? Now here, what is the relation between mobility and temperature actually here? The mu is proportional to T per minus 2. That means inversely proportional. How they related actually? Inversely proportional. Means as the temperature is increased, what about the mobility actually decreased? Right? Now here, I am going to plot the mobility versus temperature graph. That is log mu versus log T. Right? Here, in case of conductor, actually, as the temperature is increased, what about the mobility? The mobility is decreased. This is the mobility versus temperature graph in case of conductor. Right? Copy. Next topic. Temperature effect on conductivity in a conductor. Yeah. See here, in case of conductor, how conductivity is affected due to temperature. See first, tell me as temperature is increased and what about the mobility here? Decreased. Right? So mobility is decreased. Then what about the conductivity actually decreased? Why? We know sigma equal to N into E into mu. Right? If conductivity is decreased, means actually what about the resistivity increased? If resistivity is increased, it means what about the resistance increases, right? That's why the metals or conductors exhibit positive temperature coefficient. Here resistance is increased because of increasing of temperature, na? So it exhibits positive temperature coefficient. That is delta R by delta T is nothing but change in resistance with respect to temperature is nothing but what actually positive. See, with respect to resistivity and resistance, it exhibits positive temperature coefficient, and with respect to conductivity, okay, the conductors of metals exhibit negative temperature coefficient. That means here the conductivity is decreased because of increasing of temperature, right? That means the delta sigma by delta T equal to what actually? Negative. Right? This is the effect of temperature on conductivity in a conductor. Copy? Yeah. The next topic. Fermi direct function. First of all, what is a Fermi direct function actually? The Fermi direct function is nothing but it's a probability function. What it is? It's a probability function which is used to find out the probability of an electron in allowable energy state. Which is used to find out probability of an electron in an allowable energy state. Right? So here the Fermi direct function is can be expressed as, that is, f of e equal to 1 by 1 plus e power minus of E minus EF by kT, right? Where E is nothing but given energy level and EF is nothing but Fermi energy level, right? So here to explain this Fermi direct function here, now I am considering the energy band diagram of a conductor or a metal. In case of conductor or a metal, actually both conduction band and valence band both will be overlapped, right? Now, this is the Fermi level for conductor. Now, this is called as empty states because all charge carriers are in valence band, right? All electrons are present in valence band. If you supply the few amount of energy, then only it will move to conduction band, right? That's why this part must be empty state and this valence band part must be filled states, right? Now here, what is the significance of this Fermi direct function actually? It's a probability function which is used to find out the probability of an electron in an allowable energy state. An allowable energy state means nothing but whether the electron will occupy the empty state or will fill state. Right? To know this one, actually we are using this Fermi direct function. Right? Here, how? See here, first consider case 1. What is the case 1 actually here? First, see the given energy level is equal to Fermi energy level and temperature is not equal to 0. Temperature is not equal to 0. Then what is the probability value here? F of E equal to 1 by 1 plus E power 0. Right? Now here 1 by 1 plus E power 0. So which is equal to what? Half. So that means what is the meaning actually here? The probability equal to half. The probability equal to half means, so electrons neither occupy the empty state nor occupy the filled state. Neither occupy the empty state nor occupy the filled state means where it will occupy? It will occupy the Fermi energy level. Yeah, that can be known with help of this function. Nothing but what is this? It's a probability function which is used to find out the probability of an electron in an allowable energy state. Right? Now, the case 2 here, the same way, if given energy level is less than the Fermi energy and the probability equal to 0 and temperature is equal to 0, right? So here if the E is less than EF, E less than EF means the given energy level is below the Fermi level and the temperature is equal to 0, then what should be the probability value actually? F of E equal to 1 by 1 plus E power minus infinite. Here 1 by 1 plus e power minus infinite is nothing but what is this actually here? E power minus infinite is nothing but what it is almost 0. Then what is the probability value actually? 1. Here the probability equal to 1 means E less than EF, probability equal to 1. That means all electrons will occupy field states. Right? Here what is the condition here? All electrons occupy field states. Yeah. How you know all electrons will occupy the field state with help of the probability function? Nothing but Fermi direct function. And the third case. What is the third case actually? If given energy level is greater than the Fermi energy level and temperature is equal to 0, then what is the probability value actually? F of E equal to 1 by 1 plus E power infinite. Then what is the probability value? 0. See, if E greater than EF means above the Fermi and probability is 0. Probability is 0 means actually means electrons will not occupy the empty state. Probability equal to 1 means it occupy the empty state. But here the probability equal to 0 means here it will not occupy the empty state. It will not occupy the empty state means where it will occupy? Field state. Yeah, this is the occupying condition. This is the not occupying condition. That means what we can say here, that is probability equal to 0 means no electron present in empty state. Yeah. This is about Fermi-Dirac function and its significance, right? Write down the first definition actually first. Fermi-Dirac function, write down the notes. It's a probability function. It is a probability function, and it is used to find out probability of an electron in a allowable energy state. Allowable energy state. Right. Mathematically, Fermi-Dirac function is given by f of E equal to 1 by 1 plus e power E minus EF by kT. 1 by 1 plus e power EF by E minus EF by kT, where E is the given energy level, and EF is the Fermi energy level. Right. I think, and we know what is kT, Boltzmann constant, and T is the temperature, right? Now put the heading case 1. Yeah. If E equal to EF and temperature equal to 0, temperature is not equal to 0, then f of E equal to write down this one, 1 by 1 plus e power 0 equal to half. That is, electrons neither occupy the filled state nor occupy the empty state. Neither occupy the filled state and nor occupy the empty state. Yeah. Next, case 2. And copy the case 3 also. Copy from the board. And copy this energy band diagram also. Yeah. Thank you. Chapter 1 is completed. That is classification of the materials. In the next lecture, I will start with chapter 2, that is semiconductor physics. Thank you.